You're listening to DTFHN for February 24th, 2026. I'm your mass-produced but individually calibrated host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people who build things argue with people who critique things until everyone learns something. Today's got that energy where elegance and absurdity shake hands and mean it. Let's get into it. The top comment on this one is perfect. An ex-electrical engineer tries the code, watches smoke come out of a shorted battery, and then says, and I'm paraphrasing, "It's horrible to use, but only marginally more horrible than using real breadboards. That's the highest compliment an EE can give." Let me play devil's advocate for a second. Several commenters pushed back hard on the 3D view. One called it unnecessary complexity, suggested it was a Vibe-coded 3.js demo. Another asked for a plain simulator without the 3D. Just show me what's happening in the circuit. Slow it down, let me learn. And on the surface, that critique lands. Schematic abstraction exists for a reason. Nobody debugging a power supply wants to rotate a virtual breadboard to find where they plug in a capacitor. But here's the thing the critics are missing. Schematics are great if you already know how to read schematics. That's a real barrier. Not an insurmountable one, but real. And the gap between understanding a circuit diagram and understanding what happens when you push a wire into row 14 of a breadboard. That gap kills beginners. Diode bridges it. You short the battery, smoke comes out. You wire an LED backward. Nothing happens. The physical metaphor teaches something the abstraction can't. Now, the engineering craft here deserves real appreciation. Simulating analog circuits in a browser is genuinely hard. SPICE, the industry standard, has been around since 1973, and it's still computationally demanding. Getting even basic component simulation running at interactive frame rates in WebGL, with realistic enough behavior that an XEE recognizes the failure modes. That's serious work. The 5i5 timer alone has internal feedback loops that are non-trivial to model correctly. One commenter mentioned to wine recode Chrome on Steam as a more mature alternative. Fair, but Chrome costs money and lives on a gaming platform. Diode runs in a browser tab. Free, no install, no account required to start building. You can share a circuit with a URL. That architecture matters. A 14-year-old in Lagos with a browser and curiosity can wire up a transistor amplifier right now. No kit to order, no shipping to wait for, no lab to access. The components are virtual, but the understanding is real. And when that kid eventually touches a physical breadboard, they'll already know that shorting a battery makes smoke. Without the burn marks. The tools exist. The browser is the lab. Someone just made electronics education zero cost and zero friction. And the main complaint from experienced engineers is that it feels too much like the real thing. Story 2 takes us from building circuits to building walls. Firefox 1.4, Win14 just shipped a native defense against one of the web's oldest demons. One line in the documentation is easy to miss. The method signature for SetHTML accepts an optional configuration object. That configuration object lets you define exactly which elements and attributes survive sanitization. It's a whitelist. And the default, the thing you get when you pass nothing, strips every script vector the spec authors could identify. Run this forward. For 15 years, the security model for user-generated HTML on the web has been, hope the developer remembered to sanitize. Libraries like DOM Purify exist. They're good, but they're opt-in. You import them, you call them. You hope nobody on the team bypasses them with a raw InnerHTML assignment at 2 in the morning during a deadline push. The vulnerability isn't in the library. It's in the gap between the library and the developer who forgot to use it. SetHTML closes that gap by making sanitization the insertion method. You don't sanitize and then insert. You insert and sanitization happens. One function call replaces two. The cognitive load drops to 0. The comments raise fair points. You can still inject arbitrary markup. Oversized headers, walls of line breaks, structural chaos. True. But structural mischief and script execution are fundamentally different threat classes. One annoys your layout team. The other exfiltrates session tokens. Conflating them misses the precision of what this API actually targets. What's worth noting is the lineage. Mozilla started pushing content security policy in 2009. 17 years later, CSP adoption across the broader web remains thin because it demands architectural discipline most teams don't have. The Sanitizer API learned from that failure. Instead of requiring developers to understand a policy language and maintain it across deployments, it hands them a single method that does the right thing by default. The security expertise is baked into the browser engine itself. And then there's the trusted types angle. One SetHTML is your standard insertion path. Enabling trusted types enforcement becomes almost trivial. You write a policy that allows SetHTML and blocks InnerHTML, and suddenly your entire code base has a compiler-level guarantee against injection regressions. The two APIs aren't just complementary. They're sequential. Adopt one, and the other becomes nearly free. Firefox 131st ships first. Chromium and WebKit will follow. When they do, every browser on every device will carry a built-in defense against the vulnerability class that sat in the OWASP top 3 since before most junior developers wrote their first line of JavaScript. The protection ships with the platform. No dependency to install, no bundle size to justify, no import to forget. It's just there. We talked about security becoming invisible. Now let's talk about programming becoming expressive. Story 3. λProlog. Indizia samtinsualism, ilan kolmaram, bil prolog in Marseille. Logic programming. The idea that you could describe what you want and let the machine figure out how to get it was radical, but Prolog had a ceiling. It operated in first-order logic, which meant it could talk about things, but it couldn't talk about talking about things. You couldn't pass a predicate as an argument. You couldn't abstract over structure itself. For a paradigm built on the promise of declarative reasoning, that was a profound limitation. 6 years before the web existed, Dale Miller and Gopalan Nadather looked at that ceiling and removed it. lProlog extended logic programming into higher-order intuitionistic logic. Church's simple theory of types specifically. And the result was the first programming language in history to directly support higher-order abstract syntax. Hey, AAS. The ability to use the language's own binding mechanism to represent binding in the objects you're reasoning about. If that sounds circular, it is. Beautifully, productively circular. You stop writing bookkeeping code to track variable scope and substitution, and let the logic handle it natively. The plumbing disappears. What makes this worth talking about in 2026 is the metaprogramming angle. lProlog is a language for writing programs that reason about programs. They're improvers, type checkers, compilers. The tools that verify other tools. Abella, the interactive theorem proverb built on lProlog's foundations, can do inductive and coinductive reasoning over specifications that manipulate bound variables. That's not a party trick. That's the machinery you need if you want formally verified software. And formally verified software is the difference between trusting a system because someone told you to, and trusting it because there's a proof. One commenter noted they had to dig surprisingly hard just to find a syntax example. That's telling. The academic paper trail is deep. Miller literally wrote the book. But the on-ramp for a curious developer is steep. The LP implementation compiled through OCaml to JavaScript, meaning you can run lProlog in a browser right now, which is a genuinely elegant piece of bootstrapping. But discoverability remains the bottleneck. The language is 37 years old. Its foundations predate most of what we now call programming language theory, and the core insight. That higher-order logic isn't just more expressive, it's more honest about what programs actually do when they manipulate structure. Keeps finding new applications. The Eindennight Gats, a paper is still worth reading. The ideas haven't aged because they were never fashionable. They were just correct. Ideas that were correct before their time have a way of finding the right minds early. ITM War, remarkably early. The strongest case against celebrating child prodigies is that we romanticize them into irrelevance. That by turning an 8-year-old into a spectacle, we miss the actual mechanism. We tell ourselves genius is lightning. It strikes or it doesn't. And that lets everyone else off the hook. Parents, institutions, entire education systems get to shrug and say, well, he was just born that way. Nothing we could have done differently. It's a comfortable story. And this 1984 paper dismantles it. The question nobody wants to sit with is this. How many Terence Taos did we lose? Not because they lacked the neural architecture, because nobody did what Billy and Grace Tao did. The paper describes parents who didn't push. They observed. They watched a 2-year-old teaching 5-year-olds from Sesame Street, and instead of panicking or bragging or enrolling him in some accelerated program designed to optimize test scores, they did something radical. They paid attention. They let the kid follow the curiosity where it led. By 7, he understood a billion groups. By 8, he was graphing cubic functions in under a minute and working through university textbooks. The instinct is to gawk at the numbers, but the paper's real contribution is documenting the environment. The parents who treated their child's intellect as something to be stewarded, not showcased. The teachers who bent the system rather than forcing the kid to fit it. One commenter draws the parallel to John Stuart Mill. Greek at 3, Plato at 6. And Mill himself wrote about the psychological cost of being treated as a performance rather than a person. Tao's parents somehow threaded that needle. The flowers for Algernon comparison in the comments is haunting for a different reason. Charlie Gordon's tragedy isn't that intelligence fades. It's that the system surrounding him never adapts to who he actually is. That's the default experience for exceptional kids in standard education. The system isn't built for them. It's built for the median. This paper is from 1984, 41 years ago. The insights about individualized pacing, about letting passion lead structure, about the difference between acceleration and enrichment. We had the data. We've always had the data. The question that hangs over every page is not how Terence Tao became Terence Tao. It's how many kids with that same spark sat in classrooms where nobody was paying attention, where curiosity met a curriculum that had no room for it, where the answer to a child who already understood calculus was sit down. We're doing long division today. The tools exist. The knowledge is available. It's been available since at least 1984. The bottleneck was never capability. It was willingness. The willingness is showing up in unexpected places, like a developer who just built a distributed queue out of a single JSON file. A single JSON file. That's the queue. Not Redis, not Kafka, not some managed service with a pricing page and an SDK. One file on object storage, overridden with compare and set, and it handles distributed job scheduling with FIFO ordering and at least once delivery. Run that forward. Turbo Puffer needed a queue to notify indexing nodes when to rebuild search indexes. Their old design sharded work across nodes, which meant a slow node became a bottleneck for everything assigned to it. Classic head-of-line blocking. The fix? Rip out the sharding. Put every job in one file. Let any idle node claim the next one. The elegance is in what they didn't build. Compare and set on object storage gives you atomicity without lux. You read the file, append your job, or claim the next one, write it back. If someone else modified the file between your read and your write, the write fails, you read, you retry. That's your entire concurrency model. No distributed consensus protocol. No leader election. No zookeeper. The throughput problem is real, though. Object storage writes take up to 200 milliseconds. One request per second on GCS if you're writing jobs individually. Their answer is group commit. Buffer incoming requests while a write is in flight. Flush the whole batch when it lands. Same technique databases have used for decades to coalesce FIC calls. Proven pattern. New substrate. Then they add a stateless broker. The broker doesn't own the queue. It's just a process that reads the file, batches operations, and writes it back. Any broker can do this. If one dies, another picks up. The queue file is the single source of truth, sitting on infrastructure that already handles replication, durability, and availability. One of the commenters nailed the dynamic perfectly. Object storage solves most of your concurrency problems for you, handing you semantics that just work. The trade-off is single file throughput, and group commit handles that. What makes this worth paying attention to is the design philosophy underneath it. They started with the simplest thing that works and added complexity only when they hit a wall. The final system cut tail latency by 10x. The architecture is a JSON file and some batching logic. The infrastructure we already pay for. Object storage, Kubernetes, global replication. Turns out to be a remarkably good foundation for things we keep over-engineering. Sometimes the sophisticated move is using less. We talked earlier about tools hiding in plain sight. Here's one that's been hiding in your terminal this whole time. MIT has been teaching this class since 2020, and the fact that it still needs to exist tells you everything about how computer science education works. 6 years later, students still graduate knowing how to implement a red-black tree, but not how to rebase a branch. The course is called The Missing Semester of Your CS Education. Shell scripting, version control, text editors, debugging tools. The stuff you actually use 8 hours a day for the rest of your career. The stuff that separates the engineer who solves a problem in 10 minutes from the one who spends an afternoon copy-pasting from Stack Overflow. For the 2026 revision, they made a choice worth examining. Instead of bolting on a standalone AI lecture, they folded AI tools directly into every topic. Want to learn about shell scripting? You also learn when to let a language model write the pipeline for you, and when that's a terrible idea. Version control? Here's how AI-assisted commits work. And here's why you still need to understand the directed acyclic graph underneath. The integration is the point. AI isn't a subject, it's a layer. One commenter asked whether this is Anthropic buying its way into the curriculum the way Sun did with Java in the 90s. Fair question, but look at the architecture of the course itself. Every lecture is freely available on YouTube. The notes are open. Community translations exist in dozens of languages, and they're actively soliciting pull requests. The course material is MIT licensed. Anyone can fork it, adapt it, teach it at their own institution. That's not vendor lock-in. That's infrastructure. The deeper issue is that one of the commenters flagged. A large enterprise client requires 18 hours of Agile training plus 14 mandatory online courses. Meanwhile, the skills that actually compound fluency with your editor, your shell, your version control system get zero formal instruction. We train people in methodology and starve them of craft. What MIT is doing here is putting the tools where people can reach them. Free lectures, open materials, no paywall, no certification racket. The revision acknowledges that the toolbox changed without pretending the fundamentals don't matter. You still need to understand what your shell is doing. You just also need to know when to delegate. The course exists because institutions won't teach this. The fact that it's open means institutions don't have to. Anyone with a browser can start tonight. Open tools are great, but they need open secrets management to match PAWS, and someone just built exactly that. I spent a week last year debugging a credential leak, not a breach, not a sophisticated attack. Claude read my .in file during a refactoring session, and helpfully included my Stripe key in a code suggestion that got committed to a branch. Caught it in review, but the window was open for 6 hours, and that's 6 hours too many. This is the problem enveil addresses, and the engineering is worth admiring. Your .in file becomes a map of symbolic references. EV://database_URL. EV://stripe_key. Plain integers and non-sensitive config stay as literals. The actual secrets live in an encrypted binary store, local to the PyJect, never touched by any tool that reads your file tree. Let's break down what's actually happening under the hood. When you run enveil run, it prompts for a master password. Never echoed, never in shell history, never passed as a command line argument. From that password, it derives a 256-bit AES key using Argon 2 GRE with 64 megabytes of memory cost and 3 iterations. That's not a casual choice. Argon 2 EE is the current best practice for password hashing precisely because it's expensive to parallelize on GPUs. The store itself is AES 256 DCM, with a fresh random nonce on every write. So, you get authenticated encryption. Flip a single bit in the ciphertext and decryption refuses entirely. After resolving the references, the key and password bytes get zeroized from memory. The subprocess inherits the real values in its environment, and the parent process forgets them. Now the comments raise a legitimate point. Any process running as the same user can inspect the environment of a child process. That's a real limitation, and the author doesn't hide from it. But the threat model here isn't defending against a malicious local process. It's defending against the ambient reading that AI coding tools do by default. Scanning your project directory, ingesting context, occasionally surfacing things you never asked them to surface. The tool is written in Rust. It's open source. It has 0 third-party service dependencies. Philipric's original approach used 1Password as the backing store, which works but introduces an external dependency and a subscription. Enveil gives you the same architecture self-contained. Cargo install, enveil init. Start setting secrets. What I appreciate most is the restraint. This isn't trying to be a secrets management platform. It's solving one specific problem. prAIng takes secrets sitting in files that AI tools read and solving it with solid cryptographic primitives, the right tool at the right scope. We talked about running models on your own hardware earlier. Story 8 takes that spirit to the firmware level. What does it actually cost to own your own computer? Not the purchase price, the real cost. The hours spent understanding what runs beneath the operating system, beneath the drivers, in that layer of firmware, most people never think about and fewer people ever touch. There's an analogy from organ building. For centuries, pipe organs were the most complex machines humans constructed. Every builder understood every component because the knowledge was shared across guilds. Then electronic organs arrived, sealed units with proprietary circuits. And suddenly, the person who played the instrument couldn't maintain it. The complexity didn't decrease. The access did. Your laptop's BIOS is that sealed organ. Intel Management Engine runs code you cannot audit on a processor. You cannot disable. With network access you did not authorize. This is not a conspiracy theory. It is the documented architecture of every modern Intel system. A developer going by Dork just ported Coreboot to the ThinkPad X270 in under a week. The process is instructive. Dump the existing BIOS with a clip-on programmer and a $4 microcontroller. Extract the Intel flash descriptor and network configuration because those regions are necessary for the machine to function. Apply dguard patches to neuter the management engine. Then write new auditable firmware back to the chip. Along the way, a capacitor got knocked off the board and launched into oblivion. A $10 data key order, a schematic reference, and solder work fixed that. The X270 differs from the already supported X280 in specific ways. No Thunderbolt, a SODIMM slot instead of soldered RAM. A different embedded controller. Each difference required reading Intel pin documentation and making deliberate choices about GPIO configuration. This is unglamorous, patient, technically demanding work. No venture funding, no product launch. One person with a flash programmer, cross-referencing schematics and chipset documentation, making the machine answer to its owner instead of its manufacturer. The comments surface a practical question. The X270 throttles its processor when you install a third-party battery. That behavior lives in firmware. When you control the firmware, you control the answer. Every machine liberated this way becomes a reference implementation. The diffs are public. The next person's port gets easier. That is how open systems compound. Now for something beautifully unhinged. Someone built a working x86 CPU emulator entirely in CSS. One commenter put it perfectly. They didn't stop to think if they should. And then someone else linked a 0-day CSS vulnerability from February 2026. Which is the kind of comedic timing you cannot script. Let's pull this thread, because the community reaction splits into two camps that mirror a debate as old as computing itself. Camp 1 says, this is art, this is beautiful, this is what computers are for. Camp 2 says, this is evidence that CSS has become dangerously complex, that a styling language should not be Turing complete, that we've built something no one asked for and everyone has to maintain. Both camps are right, and the history here is illuminated. In 1000 time, denon, duon, any tiny 36, Alan Turing proved that any system capable of conditional branching and arbitrary state manipulation can compute anything computable. He wasn't making a recommendation. He was describing a boundary condition. CSS crossed that boundary somewhere around container queries and custom properties. And Lyra, the creator, decided to prove it by compiling C programs through GCC into 886 machine code and executing them entirely in style sheets. No JavaScript. The page includes a script tag for a clock, but that's a performance optimization. Disable it and the CSS falls back to its own clock implementation using animation keyframes and container queries. Zero user input required. The program runs because the cascade runs. The engineering craft deserves real admiration. This is handwritten CSS in Sublime Text. No preprocessor, no framework. A Python script handles the repetitive parts. The opcode table, the instruction decoder. But the architecture itself is someone sitting with the 8A6 instruction set reference and translating each operation into selector logic and counter resets. Most of the base instruction set is implemented. Conditional jumps work, arithmetic works. The stack works. What makes this beautiful is the same thing that makes it unsettling. CSS was designed to separate presentation from content. It was supposed to be the simple layer, but computational universality doesn't care about your design intentions. Give a system enough expressive power, and someone will build a computer inside it. Spreadsheets, PowerPoint, Minecraft Redstone, now CSS. The source is public, the techniques are documented. Anyone can read how selector combinators become logic gates. That is the difference between a parlor trick and a contribution. When you publish the method, you're teaching, not just performing. Moving on. Buried in every age verification law is a word that does all the heavy lifting. Reasonable. Reasonable steps. Reasonable measures. It sounds modest, but reasonable in practice means platforms get to decide how much of your identity to collect, how long to keep it, and what to do when their guess about your age turns out wrong. Let me play the other side for a moment. Suppose age verification worked perfectly. Suppose every 13-year-old was correctly identified and locked out. You have now built a system that knows with certainty the real identity of every person using a social platform. You have built the thing that privacy law spent 2 decades trying to prevent. The success condition and the failure condition are the same architecture. The European zero-knowledge proof approach is worth watching. Derive an over 18 attribute from an ID. Disclose nothing else. Store nothing on the platform side. Mathematically, it works, but it still requires that the person at the device is the person who enrolled. A parent hands a child an unlocked phone. A teenager borrows a passport. The cryptography is pristine. The human layer defeats it in seconds. One commenter suggested flipping the model entirely. Instead of proving adulthood, prove childhood. Flag a device as belonging to a minor. Let sites filter accordingly. Parents opt in. The default is access, not restriction. It is a cleaner architecture, because it puts control where it belongs, with the people who actually know whose hands are on the screen. The real question age verification forces is not technical, it is political. Do you build a system where platforms know who everyone is? Or do you accept that some problems cannot be solved with identity infrastructure without creating worse ones? Every verification layer is a surveillance layer wearing a different hat. The engineering is straightforward. The trade-off is permanent. This has been your daily tech feed for Hacker News for February 24th, 2026. This podcast is entirely AI-generated. Scripts by Claude Opus 4.6. Voice by Quen3TTS, not affiliated with Hacker News or Y Combinator. Now go build something that surprises you. We'll see you back here tomorrow.